conversation working. So I am going to flick back every now and then and just check this message window in case I do drop off or something else goes wrong. But let me get started, and then every now and then I'll flick back over to here. So I will actually start my deck now. And what I wanted to talk about today, and originally I didn't think I'd have a whole lot of time and we'd leave lots of time for questions, which will be text questions today. And now I have even less time, so I'm going to try and be fairly succinct. But I wanted to try and make as much impact as possible in the short amount of time that we do have today. And what I thought I'd do is try and give everybody a bit of a sense of what the state of security is like on the web, and particularly the broken web, insofar as we've got a lot of stuff out there that doesn't work very well. And I've got a few things I want to show you to try and make a bit of impact in that area. And the first one is just generally how broken is the web. So how broken is stuff that is out there that you can go and observe right now or right after this, and will probably give you a little bit of a scare. The second one is how broken our developers are. So we have many people out there who have a very, low security prowess level. So many sort of very fundamental concepts not understood. And I want to show you some examples of what those are. And finally, I want to talk about devices as well. And devices are getting very interesting because we have so many internet-connected devices. And some of them have some pretty rotten security going on in them. And I think this is becoming a very sort of interesting area. So where I might start is just to try and demonstrate the ease with which we are seeing websites attacked. And I think it's interesting that often we'll see headlines in the papers about elite hackers and they're anonymous or they're lulsec or whoever it may be, as though they're some cyber army floating underground with these expert skills. And in many times, the ease with which websites are being attacked is really a little bit ridiculous. And I thought I'd give you a few examples. And the example I might start with is an example called ALMAR. And ALMAR stands for Error Logging Modules and Handlers. And this is a very, very popular library used within ASP.NET websites. And what ALMAR does is when an unhandled exception is raised in a web application, rather than just throwing an error page and then moving on and forgetting all about it, ALMAR enables that unhandled exception to be logged to a database. And it then allows an administrator to come back later on, look at all those exceptions, and try and figure out what on earth is going on. So it'll do things like store the yellow screen of death that you see on some websites that aren't displaying errors correctly. So that'll be things like stack traces and line numbers and request headers and just really, really extensive amounts of data. And what I thought I would show you, and I am going to be continually flicking out the slides here and making sure that I check everybody is still on and working. So what I want to try and show you here is the extent to which ALMAR has been insecure on the web. So I've got a few little examples here, and one I wanted to show you here, I'm just going to jump over to Google because it turns out that Google is better for finding vulnerable web applications than what Bing is. So I'll just grab a new in private session just here so it doesn't remember my old searches. Now, one of the interesting things about Google, many we hear about this term Google Dork, and inevitably Google Dorks are a good way of finding huge volumes of unprotected data on the website. So often you can carefully construct a search and find all sorts of things which the owners had no intention of you finding. Now here's an example. So this is an ALMAR log search. So almar.axt is the handler that normally exposes the ALMAR logs, and we can see here we've got 650,000 results for websites that are exposing ALMAR logs. And we don't want to go around and poke too much, but just as an example, I'm just picking the first one off the rank here, this is what an ALMAR log looks like. And then when you drill into an ALMAR log, it has all sorts of very, very useful information. Many of these have things like connection strings, usernames, passwords, enough information to go in there and basically wreak havoc on a substantial number of websites. And I wanted to show you this one because it's just so ridiculously easy. So when we see these elite hackers, sometimes it's as simple as someone knows how to do a Google search. It really is a very simple concept. So I'll jump back into my deck for a sec, and the other example I wanted to give you along these lines is around anonymous FTP. And one of the things that's quite scary on the web is that there is a huge amount of content which is available over anonymous FTP. This is not intentional anonymous FTP. And to give you an example of the sort of stuff, if we do another very carefully crafted Google search, and this time we will jump over and take a look for web.configs. So there are a huge number, and I think 3,000 plus is a huge number in this case, of unprotected web.config files that are searchable and are available on anonymous FTP websites. So again, if we take the first example, here is a case where we have a web.config sitting on a website, accessible via FTP, not only accessible via FTP, but being indexed by Google. Now, the file itself may not have too much of interest in it, but the scary bit is that, of course, this is anonymous FTP, so it pretty much allows you to browse around and find all sorts of things. And you may come across, here's an example, VPN passwords. I'm not going to click on that, given the potential nature of what may be in that file. But again, it's just an example of how readily available so much of this information is. Once you can find websites with anonymous FTP, you can start to find things like database backups which developers have put on the website. Why they do this? Well, it's convenient. It makes it nice and easy. Unfortunately, it also makes it nice and easy for people to go and attack that and grab databases with backups of credentials and customer data and all sorts of other things. So that one is a real worry. Now, there are a couple of Google Doc search examples. Another example I thought I'd give you is basically how easy it can be with automation tools to perform attacks such as SQL injection. Now, this is my son. He's 3, and we did a little video together a little while back, about 6 months ago, where he was the guy who managed to use the tool to exploit a SQL injection flaw in one of my demo websites and pull out a bunch of credentials. Now, he can drive a mouse, and that's about the extent of it, but if you can drive a mouse, you can hack a website. I want to give you an example of how simple this is. And what I'm going to do is let me go to a website of mine, safeweb.com. There's a security scanning website of mine, and one of the things I do with this is I make available a sample vulnerable website in order to be able to scan and basically give a demo of how the thing works. Now, this sample vulnerable website has got a SQL injection flaw on it. And I'm not sure how many people are familiar with the concept of SQL injection, but while this loads, in short, we pass untrusted data to websites. And if I load one of these links, that's kind of done. If we have a look at the URL, we'll see that we are loading widget.aspx, and then there's a question mark, so everything after that is obviously the query string. And we're asking for ID number 4. So semantically, we're sort of saying, hey, give me widget number 4. Now, where SQL injection comes into play is that if you can manipulate the value of the untrusted data, so in this case the number 4, you may be able to change the way the query on the database is executed. Now, what's really interesting is that if we grab that URL and we jump over to a piece of software known as Havage, and we just paste that into the target, and we start analyzing, this is sort of automation of SQL injection. So this is a free tool for quote-unquote security professionals. Based on the comments and the feedback I get on one of my blogs about this, it is probably used by a lot of people who are not security professionals. I'll give you an idea of the ease. So we've just plugged in the URL and said analyze. Now, this is a live website. When I click on the tables button here, it's come back and it said, look, you've got one database here. And the name of that database is random. It's at a shared hosting environment, and they just randomize database names. But what I can do now is say, hey, I would like to get the tables for that database. Now, what you've got to remember is that this little application is going out and hitting a website. So this is an HTTP request for a website, and it's just passing data through in such a way that it's causing an internal exception in the web application, which exposes the SQL implementation. Now, this is pretty cool. It's come back and it said, well, look, here's all the data that you have, or rather all the tables that you have in your database. So you then say, okay, great, well now I would like to get all of the columns of a particular table. So let's say the ASP.NET membership table, and we can now see all the columns appearing. And again, these are just requests to the website. The website is coughing this data up, and the party trick is that there's just a huge amount of automation. Now what we can do is say, I want to get the email address out of there, so we're now selecting columns, and I want to get the password out of there. Now go and get me the data. So what happens now, we can see the email addresses and passwords popping up here. This application is actually able to go and grab data out of the database, which is kind of scary. And you can see how a 3-year-old can do this, because all you've got to do, I mean, what do you have to know? You need to know how to copy and paste, and you need to know how to find a website that has a URL and a query string on it. And that's it, and you get data out of it. So as impressed as we are with the exploits of some script kiddies who hit the news, this is often the sort of thing that is going on. I'm just going to check back here on the text and make sure that we have no questions going. I might even stop halfway through and just check that there is no pending question or otherwise. So let me jump back into my PowerPoint. And I'll continue the presentation. Another example I thought I'd give you, and this one is just slides for the next few bits. And this is an example of another web application. In fact, it's a mobile application with the web back end that I wrote about around about 18 months ago. And what you're looking at here is a mobile application to help you find your car in the Westfield Bondi car park in case you lose it. So the theory is, it's a little bit like that Seinfeld episode you may have seen where they walk out of the shops, they cannot remember where the car is, and they go walking around and around and around for hours, not able to find the thing. The idea of this app is that you pull it out, you say, I can't find my car, you put in your license plate, and you get 4 results back that are thumbnails like what you see here. Now the idea is that the thumbnails are pretty small. So you can't make out the number plates on any of these. If we zoom it in, it's a very depixelated image, because obviously it would be a privacy risk if you could make out the number plates. So they kind of left it at this. You only get 4 so that you can't go through and enumerate them and do all sorts of other nasty things that might accidentally breach someone's privacy. Now the way these things work is they have these park assist sensors on the roof. And you've all probably seen this. You drive into a shopping centre these days, there's a great big LED sign out the front and it says there are X number of parks available. Go this way and there's 10, and you go that way and there's 20. And then as you drive along, you get these little lights on the roof so you know where to go. Now the way these things work is obviously there's a whole heap of them. They're all networked up and they're all joined back up to a server. So they're all pulling back data and storing it somewhere centrally. This is all pretty logical, it all makes sense. The interesting thing is that the data then gets exposed via an HTTP endpoint. Because these days everything's connected to the web, right? We want everything to be accessible and everything to be available to everybody. So you end up getting a URL that looks a little bit like this, which exposes the state of the bays. Now this is what the iPhone hits. So the iPhone is going off to this website, and it's asking for data on cars that match your number plate. And we'll break this down again a little bit further in a moment. What happens then is the website responds, and the website comes back with a piece of data like this. So this is just JavaScript object notation. It's a bit of JSON, which is the language that most mobile devices work backwards and forwards with web servers on. The interesting bit, though, is that the underlying data actually has the license plate of the car. So the objective of obtaining privacy through using low-resolution depixelated images is sort of undermined by the fact that you've got this data stream going backwards and forwards to the phone that actually discloses the number plate. Now, what a lot of people don't realize is all of the HTTP communication between a mobile device or any device and a web server can be very easily intercepted. So an easy way, for example, would be if I run a proxy on my PC, and a good example of that is something like Fiddler Proxy, and I set my iPhone to connect to that proxy, and this is all at home on my own network, every HTTP request I make, I can intercept via that proxy. HTTP is not meant to be a secure communication channel. HTTPS is, but that's another story, and that's not how a lot of these services work. So moving on, what happened next is if we break down this URL, we can see that it consists of a number of parameters. So, for example, we can see that there is a line there, and I've just struck it out, where the number plate has passed through. Now, if we take that out, these are like filter parameters. So if we take out that parameter, then suddenly we're not filtering by the number plate of ABC123 anymore. That filter criteria is removed. So now we're going to get 4 results back in whatever order they order things by on their back end. If we change the limit to 40, we can get 40 number plates back. And we could get all of this data back, all in HTTP, all unencrypted, all publicly accessible by anyone who can make an HTTP request, which is basically all of us. However, if we then take that guy out as well and we remove the limit, we can start to get huge amounts of data. In fact, you could get 2,550 records back from the shopping centre. Now, you've got to consider the potential for evil doings here. It makes it extremely easy to monitor all of the ingress and egress of every single vehicle to the shopping centre, because you can hit this every 60 seconds, if you like, and get around about 2,500 records. So maybe you're a competitor and you want to look at the traffic the particular shopping centre is getting at particular times of day. Maybe you're a stalker and you want to see if your victim has arrived to work or not at the shops. There's a bunch of really nasty stuff that can be done. So it's really a very sort of bad privacy design. Now, what was really interesting out of this as well, I did speak with Westfield after this was discovered and ended up talking to the developers. And I sort of said, look, why'd you do it? And the answer is basically, look, it made things very easy. So they had this one set of web services that they could use for any purpose between actually performing administrative duties and sensor management over at Westfield and Bondi, all the way through to someone who's just lost their car and they want to fire up the iPhone. And hey, we can use the one web service. Isn't that convenient? So the real moral here is that mobile devices in particular are sending a huge amount of data backwards and forwards. It is usually interceptable, and it is very frequently not designed with security in mind. So that is a massive concern. Now, just before I go on to the second section, I'm just going to flick over my link window because, again, I'm kind of talking to myself. I want to make sure that first of all, everything's good, and second of all, if there are any questions on that first section, I can answer before I move on. So I'll just give everybody a moment. Robert's happy? Everybody's happy? Okay, let me move on. And at this rate, we will have a little bit of time at the end, which is good. Okay, so the next bit about our developers. And, ultimately, things like the Westfield situation, yes, they're up there, they're live, they're in production, they're vulnerable, but in my mind at least, it really boils back to who are the people that are building our websites. There's certainly an element of, do we have the processes around things like, are we having post-release security reviews of live websites, making sure the configuration is right. Even earlier on, are we having a secure software development lifecycle? Are we having code reviews? Are we doing all those sorts of things? But at the end of the day, in my mind, it's still the guys who are sitting down in their Visual Studio or whatever IDE it is they're using, building applications that just fundamentally don't understand some very important security concepts. And I think really it's not that different to, say, fundamentally not understanding that we shouldn't be sending huge amounts of data down the wire on a request. We want to minify our JavaScript and compress our images, all these other things. They're good practices. The difference is, rather than getting a few too many bytes down the wire, you get your website owned. And that is a really rather unpleasant place to be. I want to look at some examples of some of the things that I'm seeing with developers out there and some of the misunderstandings. Some of these will give people a bit of a surprise. And the example here is, this is a question that was on Stack Overflow. And it's a fairly reasonable question. So effectively someone's saying, look, I want to store some credentials. How do I store it securely? So how do I apply encryption, or probably more appropriately hashing, but some form of cryptographic storage? So pretty reasonable question. Now the problem with crowdsourcing information is that you get answers like this. So the first person who answered this question said, okay, right, here's what you do. You get your string, you encode it into a byte array, and then you actually base 64 encode it. And the problem is that this is not encryption, okay? So this is base 64 encoding, and base 64 just gives us a way of taking a byte array and representing it with ASCII characters. So base 64 is great if we want to make sure that we can, say, append characters to a URL, or whack them into a cookie, or even store them in a database column. You know, it's a good way of getting a common baseline for the way we store data. But the thing about base 64 encoding is that you also have base 64 decoding. So if this guy is storing his passwords in this fashion, thinking that they are encrypted, it's going to take literally about 2 minutes for someone to get this and base 64 decode it and end up with the plain text. And that is just a fundamentally important problem. But I'll move on because there are a few more answers. So the second answer said, okay, well, here's what you do. You get the input string, and in this example, it's the string on the first line. And then what you do is you get the ASCII character, or rather the ASCII number for each character, and you increment it by 5. So this is called character rotation. So if you have an A, you turn it into B, C, D, E, F. So every A becomes an F, every B becomes a G, and so on and so forth. So you're basically just offsetting 5 characters in the alphabet, or in the ASCII table as it may be, because you get to Z and you're going to get high numbers. And again, the problem with that is that if you take the output of this process and then you go back 5 characters, you're back where you were before. So this is not encryption. This is character rotation. And we have schemes such as ROT13, where you actually rotate 13 places of the character set, that, again, they're barely even obfuscation. They're certainly not cryptography. So people storing credentials this way, thinking they're safe, are unfortunately a fair way off the mark. Then there's another answer, and this guy basically had the same idea. Now, what really worried me about this is you sort of get the sense, reading through these examples, that people didn't just sit there and write these answers out. I would take a very good guess that they have gone and grabbed this code from existing applications, dropped it into their Stack Overflow answer, and here we are. And I guess what kind of scares the hell out of me with this is that we've got a lot of code out there that works this way. There are a lot of applications that think they're storing passwords in a cryptographically secure fashion, and really they're just base 64 encoding them or character rotating them. And the developers don't know any better. So in the first section, we looked at how easy it was to find risks or exploit existing websites. This section is really showing us how much misunderstanding there is in so many cases about how to actually do fundamentally basic security things. So I'll go on. Another one that I saw just the other day, and this was a government website, unfortunately, in the US. When you tried to sign up for an account, and someone sent me to this, I didn't have any reason to sign up myself, but when you tried to sign up, it would come back and tell you somebody else was already using your password. And there are a few sort of fundamentally odd things about this. So the first is, the right way to store passwords is using what's referred to as a cryptographic hash. And a cryptographic hash is a one-way process. So if you provide your password in plain text, it will go through this cryptographic hashing algorithm and it will come out the other end as a cipher, which is not reversible. What that means is that the only way you can get someone to log on is they've got to provide that same input string. It'll get hashed and get the same result, because a cryptographic hash is deterministic. You'll always get the same result no matter where it runs, and you compare the output of the two. You can never get it back the other way. So the first thing that something like this tells us is, hey, these guys are not hashing their passwords. At best, they're encrypting them, and they're probably in plain text. The problem if they're encrypting them is it also means they have the ability to decrypt them. And for passwords, that's something that 99% of the time we just simply don't need to do. So it tells us right away that there's something wrong with the way they're being stored. The other thing is there's a bit of a logic flaw, because really what this starts to do, or a logic risk at least, is that it starts to make it very easy to build up a profile of the passwords in the system. There are many, many password dictionaries out there. And by password dictionary, I don't mean like an Oxford or a Cambridge or something. It is a list of words that are common passwords, so strings. It'd be extremely easy to start feeding that into a system like this and seeing how many of them land a positive. So, you know, feed in the top 1,000 password dictionary entries and you could automate it. How many of these are actually used? Okay, great. Now we've got one that's actually used. Then there are multiple ways of enumerating through the accounts in the system. So now you can start taking accounts and just throwing known passwords at it. So it makes it extremely simple to start exploiting a system. And this is just the strangest thing. I guess the third point is, you know, who cares? Who cares if there's already somebody else using the same password? The idea is that usernames are unique, not passwords. It doesn't matter if two people have the same password. There's really no impact whatsoever in that situation. So a very odd sort of misunderstanding. The other one I thought I'd show you, and I'm going to have to talk about this because the demo is on the other PC that couldn't connect a link. An example here is Black & Decker, and in fact I wrote about this on Monday night. It's on troyhunt.com. It's the last post. Black & Decker, and there's also another one in Australia, Aussie Farmers Direct, who do the same thing. Now what both of these organisations did is, like many organisations, they said, look, when somebody logs to our website, we want to give them a little tick box, and it's going to be called Remember Me, and if they tick that, the next time they come back, they don't have to log in again. It will remember us. This is always going to be the sort of feature that, even if implemented very securely, so something like Facebook, I suspect they've done a very good job of, but even if it's implemented very securely, it's always a trade-off between security and usability. So if you tick that box and someone else sits down at your PC next week, they get to log on as you. If you don't, then you've got to enter your credentials again. So it's not sort of a good thing security-wise at the best of times. What Black & Decker and Aussie Farmers Direct did, though, is they decided that the way we're going to implement this is that when you go to log on and you tick that box, we're going to store your username and your password in a cookie. Now, the thing about storing it in a cookie, and it's in plain text in a cookie as well, there's no attempt at cryptography. The thing about putting it in a cookie is it means that every single time you make a request to that website, that cookie gets sent back across the connection. In many cases, it gets sent across an unencrypted connection. So if you are on a network that's been compromised or an attacker is able to mount a man-in-the-middle attack, they can get that password on any single request, not just on your login. The other thing is that cookies have other risks as well. So, for example, Black & Decker had exposed LMAR logs. So we looked at LMAR logs a little bit earlier on, and LMAR logs, along with all the stack trace data, they also store all the request headers, and cookies are part of the request headers. So what this meant is that because Black & Decker decided to do their Remember Me feature by storing a password in a cookie, and they had exposed LMAR logs, every time there was an exception in their system caused by someone who asked the website to remember them, you had their username and their password in there in plain text. They had about 55,000 entries on their website, all public, all discoverable by Google because of that decision. Aussie Farmers Direct have cross-site scripting flaws on their website. When you have a cross-site scripting flaw, it's very easy for an attacker to obtain a victim's cookies if they can get the victim to follow a link. And there are all sorts of social engineering techniques that might allow an attacker to do that. So that was also a fundamentally bad situation. And unfortunately for them as well, despite multiple private contacts, they decided that because they haven't been hacked before, it's not really a risk and they're not going to worry about it. So I take it that they're not too concerned about me talking about it either. But, you know, again, it's just sort of an example of the fundamental misunderstandings of how these security implementations need to be done. And the solution is actually exceptionally simple, and it's just to keep the session alive. So to keep the session cookie or the authentication cookie alive for however long you think a Remember Me feature should last, a week, a month, 6 months. So there are easy constructs to do this, but developers don't always get them, and they just create these gaping big holes in the security. Now, the third section that I wanted to talk about was around devices. And again, devices are very interesting because now we have the Internet of Things. And the idea of the Internet of Things is that everything needs an IP address, and it needs either an Ethernet jack or it needs a Wi-Fi adapter because we want to talk to all our things. So what do I mean by things? Well, here's a good example. So TrendNet cameras. Now, mind you, these are probably not sort of the ultra-modern Internet of Things, and we'll look at some of those in just a moment. We've had IP cameras around for quite a while. The TrendNet ones have been very popular because they're quite cheap. People set them up as baby monitors, or they set them up to watch the house and make sure nobody's breaking in. They set motion sensors and all that sort of thing on them. Let me show you the interesting thing with TrendNet cameras. And I'm just going to grab one of my links out of here. We'll just jump back into here again. The problem with TrendNet cameras is they had a rather pleasant authentication bypass risk, which allowed them to basically be exposed to anyone. And as generally happens on the internet, as soon as there's something interesting, there's a Twitter account pop up to do it. And there's one called TrendNet Exposed. And in fact, we can see this is pretty up to date. The latest tweet was 18 minutes ago. But what TrendNet Exposed does is it just reports on all the exposed cameras. And, you know, these guys have got over 2,000 tweets here of, here is a camera, here is the IP address it's on, because inevitably these are people's home cameras, they're on their static IP addresses. And here is, you can see the path is pretty much the same if we look down towards sort of the, I won't look in this person's living room today, so it's always the same path that is at risk. Hit that and you get someone's living room, for example. And they've uploaded some of the photos here, so here's a couple of guys laying back on the couch. Their TrendNet camera is probably sitting over there on the table watching them. I would hate to think the sort of things that would be exposed and visible on TrendNet cameras, but I can take a pretty good guess. So this is the problem, right? We want to get these devices connected. We want to make them accessible. We want to give people this sort of ease of access, and security is something that we try and do if we get the time and we know how to get it right, which obviously doesn't always happen. So TrendNet is a bit of a worry. There are other examples as well. It's not TrendNet. Another example, and this is the one that's a lot more scary, and it's almost the stuff of fiction, SCADA, so these supervisory control and data acquisition devices. So Siemens makes SCADA devices, and basically these are programmable logic computers. And what a PLC does is it will do anything from manage a nuclear power facility through to water treatment through to electricity statements. Basically, this is what manages the robots and the machines that power a lot of our utilities. And it was a SCADA system as well that Stuxnet was targeting. So many of you have probably heard of Stuxnet, which was almost undoubtedly US and possibly Israel backed and designed to attack the centrifuges in Iran to try and push back the uranium enrichment activities, which it seems to have been very successful at. So it's rather scary sort of stuff. And if we can start to infect these SCADA systems, and it does appear that many of them do appear to be at risk, you know, the potential for damage is really quite scary. And the thing is, a lot of these are sitting out there on the internet, and they're searchable as well. So I'll grab another link here. It's my last link from the lot. If we jump over to Shodan, and Shodan is a search engine for devices. So Shodan allows you to search for basically anything connected to the internet. Now, whether that be a TrendNet camera or whether that be a nuclear power plant, if it's publicly facing, it's discoverable. And we can see that there are a bunch here that have been found by Shodan. Shodan also has some subscription services and you get a lot more information. But now, you know, you think back to those Google docs about finding Almar logs and finding anonymous FTP. Being able to find freaking SCADA systems that are publicly facing is taking that to a whole new level. And that is a little bit scary. So that was SCADA. The other interesting thing is that we're getting a huge array of different devices that are getting connected. So this is this Internet of Things again. And I'm almost a little bit torn between on the one hand being exceptionally cool, and I really like the idea of being able to control all my lights from my iPhone while I'm sitting on the couch, and that doesn't have to be the couch at home, it could be a couch on the other side of the world, and a bit horrified by the concept of the sort of devices and information that is being exposed from the sanctity of my home to the outside world. So lighting is one. Philips have got a system where light globes literally have little radio signals in them. They connect to a base station. They're then connected to Wi-Fi. You can sit on your couch and do things like, I want to make all my lights green or red or a different color, or schedule when they go on and when they go off. You know, again, kind of cool, but all of this is happening over IP. It's all possible to orchestrate remotely. So there is a publicly facing interface. The other one that's possibly a little bit more serious is a product called Lockytron. And Lockytron aren't the only ones, and I've no reason to think that Lockytron have got existing vulnerabilities, but we are now talking about a device that unlocks your door. And the promise of this one is that it fits to existing deadlocks. So you can see this little blue device that does have a physical knob that you can turn as well, but it's also got a little Wi-Fi device in there, connects out via the internet, and you can do things like you've got a friend coming to visit and they get to your front door and they call you up and they say, hey, can you let me in? And you press a button on your iPhone and voila, your door opens. You can also have Lockytron unlock it for you remotely if you forget your keys. And I guess the interesting thing about that is that now we're starting to say, okay, well, there is some central hub somewhere that has the ability to remotely control your door. It's not like an end-to-end encryption between your iPhone and the door. There is someone else who is able to orchestrate that process as well. So you kind of wonder, you know, how many Lockytron devices are out there or equivalent, and if these guys do get owned and their central administration systems do fall into the hands of people that want to do some damage, you know, how hard would it be to enumerate through all the doors and just unlock them all remotely? I don't know. I mean, certainly certainly we have the technology. Perhaps even worse, though, is when we start getting into medical devices. So this is an insulin pump, and similar sort of things are popping up with pacemakers where they are remotely orchestratable. So whether that be via near field, so whether they are working on frequencies that require, say, a doctor to have a device which can remotely interact with them, or whether they're now starting to get to the point where they're remotely accessible over long distances. And this really does start to become stuff of fiction. What's interesting, though, is that there have already been researchers who have shown how to hack insulin pumps to deliver fatal doses of insulin. There have been other researchers, a guy called Barnaby Jack, who did a demonstration down in Melbourne recently about doing a similar sort of thing with pacemakers, so controlling a pacemaker or hacking a pacemaker and causing it to do adverse things which could result in very serious health conditions. So, you know, you think about the damage you could do if you can control someone's insulin or if you can control their heart. And that is a very worrying situation. Now, put that together with the previous two sections on some of the understandings that many of our developers do have, as well as the prevalence of risk that stands out there on the internet, and you start to get a bit of a sense of where this could all go. This one is as much for humour value as anything else. I'm not entirely sure why you need an iPhone toilet, an iPhone connected toilet. I don't know that it's the sort of thing that you want to be able to remotely orchestrate. The idea of what you might need to do holding an iPhone when you're in the sort of proximity to benefit from it is a little bit beyond me. But I think, you know, it's kind of funny insofar as showing the extent to which everything is getting connected. Of course, this is in Japan where there is lots of technology and there is lots of high-tech toilets as well. So I just found it rather interesting. And, I mean, crikey, if we're getting iPhone-connected toilets, where does it go from there, right? Now, the last thing I thought I'd show you, and I've used this in a few demos recently because it just makes for a very, very cool demo. And it's a much better demo in person, so I'm just going to have to try and explain what it does here. What you're looking at here doesn't look like a pineapple, but it is called a pineapple. And this little box is about the size of a cigarette pack. Obviously, it has an aerial, it has a Wi-Fi adapter in it. And what this does is it acts as a Wi-Fi hotspot. So you can set this up to basically broadcast as my free wireless, if you like. You can bridge the traffic through to, say, a laptop, or you can just plug it straight into a Wi-Fi dongle, which has direct internet access, and you can effectively route other people's traffic through the device. So you set up in a cafe, you broadcast free Wi-Fi, people come in and they go, hey, here, I'd like free Wi-Fi, and they connect through to this, and now they're routing their traffic. Now, the interesting thing about this from an application security perspective is when applications don't properly protect their traffic over HTTPS, and the Westfield app was a good example, any of that traffic is readable by an attacker, and it can also be manipulated by an attacker. So if you're an attacker sitting in a coffee shop broadcasting free Wi-Fi, a victim tries to log onto a website that doesn't use HTTPS, it's extremely easy to grab their credentials. The other thing is if they do it improperly. So here's an example of where HTTPS is often used improperly. You go to a website, there's a login form, it asks for your username and password. That login form is loaded over an HTTP connection, so no security. But the developer thinks that they've done a good job because they're going to make sure that when you submit that form and your username and password is sent, it posts to HTTPS. What that means is that when it posts, you can't intercept the username and the password. The thing about HTTP, though, and the thing about a man-in-the-middle attack, is that when that login form is loaded, an attacker can do things like change the location it posts to. So it doesn't have to post to a secure connection. They can change it to post to their own website. And once that happens, it's game over. The credentials are stolen. So that's if you set it up as a rogue wireless hotspot. What's really interesting about this device, though, is a little feature it has called Karma. And the idea of Karma is that for all of us, all of the wireless devices we have, our phones, our tablets, our laptops, we've all got networks that they remember. So when we come home, it automatically connects to our home network. We get to work, it automatically connects to our work network. Our devices know all of these connections. Now, what actually happens is when you're walking around with your device is broadcasting the SSIDs that it would like to connect to. So it's effectively shouting, hey, here's my home network there, here's my network there. Are all of these other networks which I've previously connected to out there and available? Now, if one of those networks is not a secure network, this little device can come back and say, I'm going to broadcast the name of your network, and your phone will automatically connect to it. So you don't even have to take it out of your pocket. It's broadcasting the network it would like to connect to. The Pineapple receives that and says, I'm going to spoof it, I'm going to create a network that looks just the same, and your device automatically connects, and now it's sending traffic through there, and it can attack it. Now, as an example of this, I did a conference down in Melbourne a couple of months ago, and I was speaking on the second day. So on the first day, I walked around with my Pineapple with its little battery pack on it, which looks way too much like a bloody bomb, to be honest, but you put it in a bag and you walk around, and at the end of the day, it's only the size of a cigarette packet. And these are some of the networks that it picked up. So these are the sort of SSIDs that people were broadcasting. Now, I've got 315 of these walking around a conference room with a few hundred people in them. The kind of cool ones I highlighted in red. But the interesting thing is that these are all the networks people were trying to connect to. Many of these devices then connected to my Pineapple and tried to communicate backwards and forwards with whatever it was they were trying to do over the internet. And of course, as we know, our devices are always talking over the internet, even when we're not actively doing something. It's connecting to internet, or connecting to email, or doing all sorts of other activities in the background. So all of this was happening automatically. What I ended up doing with the Pineapple is just returning a little web page. So effectively doing a man-in-the-middle attack of fairly innocent intent. So, you try to load, in this example, stackoverflow.com, and instead of getting stackoverflow.com, the Pineapple returns another page. So effectively, it's DNS spoofing. It's saying, okay, you're after this URL, I'm going to return you on this URL the content from somewhere else. And it's got its own little built-in web server that could do this. Now, when it can do this, it can also do things like steal cookies. Because when someone makes a request to somewhere like stackoverflow.com, if they're logged in, it will send the authentication cookie, which keeps them logged in when they go back there again. Now, when you have a device like this, which can pretend to be Stack Overflow, it can steal those cookies. And because Stack Overflow doesn't use SSL or HTTPS, those cookies are happily sent along to the device. You can then hijack someone's session and you can go and mark down all their questions or change their profile or do whatever you like. And Stack Overflow is a pretty innocuous example, but more serious ones are probably going to be things like shopping sites with credit card details and other things of use to an attacker. So that was an example of the pineapple, and that's sort of a real-world, easily mountable attack. I know I've gone just over time. I have hit the end. I'm just going to flick back. If we have any questions or comments or anything else people would like.